Okay, so this is the first presentation of the Cyber Physical Systems course. And what we want to do, first of all, is look at all the things that we're going to be learning in the course. And so this is a major outline, a high-level outline of the course of Cyber Physical Systems, which are the chapters that we're going to cover. So in the first chapter, an introduction to systems, we're going to be trying to make a link between the mathematical ideas of things like linear systems or signals and systems and control systems to complex systems. Because not the equations, but the high-level mathematical ideas, which are still expressed as equations, but they're not solved, if you will. They are still very much pertinent to cyber physical systems. Then we're going to go into chapter 2 with an introduction to embedded computing systems, so embedded systems. And we're going to look at all the different ways of putting together an embedded systems, what they are, how can we realize different embedded systems, and what kind of approach or discipline we can adopt to help us be successful in putting together an embedded system. Now, with those two things behind us, then we can go into the actual meat of what the course is, which is cyber physical systems. Okay? And beyond that, we want to start looking at certain paradigms, technologies, or complex systems that are good examples and applications of cyber physical systems. So, first one, the Internet of Things. So you heard that everywhere. And the Internet of Everything, an industrial Internet of Things. There is a lot of terminology that we'll be learning in this course. Also, pervasive computing. So you have heard about cloud computing, but that's not all of it. You probably heard about computing at the edge or fog computing. So all these things we're going to be talking about as good example of complex cyber physical systems. Then we're going to circle back in chapter 6 and make a case for looking at the endeavor of putting together cyber physical systems as a joint venture of the classic systems engineering, but also software engineering, which have been growing at the same time and developing their own techniques, like agile development, like Scrum, all those things that by force they have had to come up with because the complexity of software has increased dramatically. But now these things are coming together because cyber physical systems, they have a great deal of software as part of them. So we're going to have a whole chapter just talking about the relationship of systems engineering, and software engineering, and how they play together to make sure that we can put and design and execute these complex cyber physical systems. And to finish, we are going to devote a chapter to what is called digital manufacturing or Industry 4.0. That's a great example of where complex or cyber physical systems find a home. And I'm not talking about what you hear in the news, well, we need to bring manufacturing together or back. That's not it. That's not actually the manufacturing that you even want to have here, okay? We're talking about complex, sophisticated, highly technical manufacturing that are going to employ things like technologies like the digital twin. So if you Google digital twin, what is digital twin? Well, that's the concept that you can have a manufacturing line, sophisticated manufacturing facility, but you can also have a model of it. You can have a digital model. And this is a virtual factory that you have, and you can configure, and it's smart, and it can reroute itself or reconfigure itself for things that sound like an oxymoron, but mass customization of manufactured products. So it looks like if you're doing something at a mass scale, you wouldn't expect it to be customized. But that is what we want. We want to be able to make products that are customizable, let's say for each customer, but at the same time have the same low-cost characteristics and high-quality characteristics of products that you mass produce. That's kind of like the dream, right? And that's one of the things that digital manufacturing or industry 4.0 talks about. So in a nutshell, that's the course, okay? Now let's dig deeper into each one of this, so you see some of the things that we're going to be talking about. So in introduction of systems, very classic, and also again making a linkage from the classic, very mathematical signals and systems and control systems to the utilization of those concepts to describe and have those concepts work for us to make sure that we understand complex systems. So we're going to look at how we describe systems and concepts of controllability, observability, and being able to identify systems. So if you don't know what a system is or what a system does, how can you, in a very formal way, put a test signal? Now this test signal could be a very complex signal. You put a signal and look at the response, and you can infer what the system is, what that transfer function is. But we're going to try to get and expand those ideas of equations into complex systems. And also things like a steady state errors of systems, which is also expanding that idea of the classic control system and linear system theory into complex systems. Now every chapter, which I'm not going to repeat in the next slides, every chapter of the book has a summary and exercises. So I talked about the exercises. It also have references for further reading that I find that they are very timely. This is also a good source, not only the case studies in some of or most of the chapters, but the references and the case studies are good sources for you to start thinking about that project that I'm going to ask you to propose per team, per pair, about halfway of the course, okay? So every chapter has that, so I'm not going to repeat that. So going to the next chapter, Introduction to Embedded Computing Systems, or just embedded systems, okay? Because normally when you think of an embedded system, what makes it a system, what makes it embedded is it has some type of embedded computing element. But we're going to talk about those systems and the different approaches. If you want a system that does something that has a specific functionality, you can realize it in different ways. And we're going to see this, the importance of specifications, because specification tells what you want to do, but it doesn't tell you how. So we're going to talk about different ways of implementing embedded systems, different hardware architectures and different software architectures as well. Important in this chapter are design metrics. How do we, so one of my favorite quotes is that you don't have to be bad to improve, okay? So think about that. You don't have to be bad to improve. So we all should be trying to improve anything that we do, and so on. So if you have a process of design, how do you improve something? Well, the key to improving something is to measure it. So you can quantify it, and then you can devise some strategy, change something, some variable, and that's at the heart of the design of experiments and the scientific method. You change something and then you measure it again. So you know if it works. If it works, great. You adopt it. If it doesn't, you ditch it. And you want to know that as soon as possible, so you don't waste your time and your efforts. And to do that, you need to measure things. So we're going to talk about design metrics in the context of embedded systems. What makes a good embedded system, a high quality embedded system, a reliable embedded system in a system as of itself, and also the process of developing that embedded system. One of the most important techniques to come up with a good execution in embedded systems is hardware-software co-design. So we're going to spend some time talking about that, maybe more than the other techniques, because to this day, a lot of teams are waiting for the hardware to be done to start developing that software, without understanding that these are symbiotic activities. It may be that if you don't think about hardware-software co-design, you don't do a good software-hardware partitioning. And how do you know what are the functions of the system that are better done by software or by hardware? So you come up with an optimal design. You have to do co-design for that. You have to be looking at both things at the same time and using techniques of rapid prototyping to be able to do it. It also saves time. Okay? The software people don't have to be kind of doing things that are not core to the project, waiting for the hardware to come out. Okay? That's still done a lot, by the way, unfortunately. So we're going to talk about formal methods of hardware-software co-design. Because like we said, these systems have a lot of complex hardware and a lot of complex software. So that's chapter 2. Then in chapter 3, we're really going to get into the design of cyber-physical systems as kind of a new body of knowledge that is trying to put all this together and all these technologies together. What are the main recommendations that the people that are looking at this closely are putting together as ways to go about designing, bringing to life and executing cyber-physical systems? How can we best capture the requirements? That's very important. Capturing requirements is very important. And then we're going to look at some applications and in more detail, things like smart cities. That's a complex system. And the Internet of Everything. So Internet of Things, industrial Internet of Things. We're going to talk about that so much that we're going to devote a whole chapter to it. Where we're going to talk about the key technologies present in what you hear about a lot in the news, the Internet of Things. So connectivity is at the heart of that. But not only connectivity via radio frequency for identification, but also to network sensors, those edge devices. And I use sensor in the broadest sense. So we could be measuring and sensing and logging all kinds of things, all kinds of data. And that gets back into big data, which is another thing that we have heard about. Another technology that is very important is RFID. RFID for asset tracking, asset management, inventory tracking, payment systems, identification of human beings. So RFID is actually a key technology and a very heterogeneous technology, which is key to the Internet of Things paradigm. A lot of what's going to make this possible, because this is just starting. If you hear about the business people in technology, they're kind of seeding and investing in companies that are going to make all this happen, and hoping that, I'm pretty sure, since they're investing, that this technology is going to grow. Well, they're talking 2020 to 2023. That's the growth. Oh, that's where you're gonna be out there. You're gonna make that happen. So that's exciting. Okay, 5G. You've been hearing about it for a while. It's 2020. 5% of the country is going to have 5G. You have to revamp everything. If you think about the technology, now it's going to give us wild bandwidth to make all this connectivity happen. But the infrastructure has to be recapitalized. Okay? And everybody's working on 5G, but really, two guys only have the money, AT&T and Verizon. So they have to do it. And it's going to take them a long time. And I hope that they take good steps and they take a good systems engineering approach so they get it right. But it's going to take 2023 is when really you really start feeling the availability of 5G, where you're going to be able to manipulate the spectrum not only in the frequency domain, but in all kinds of modulation techniques. But also, one that is going to be cool about 5G is that beamforming technology. So now you have all this frequency and all this modulation, but now you're beaming, the beam is directed. So you have what is called this multiple input, multiple output systems, MIMO. And now you can basically direct the beam to actually get more separation of information and send more information. Easier said than done, right? So it's going to take some time. You can see, because it's complex. But that's the communication backbone of all this. So it's in its infancy. And it's a good time to start learning about it and thinking how we can get involved and contribute and do some really cool things. Okay? Then we're going to have a chapter on pervasive computing. Okay? Pervasive computing, people at different levels, people have been looking at that for a while. It got us to cloud computing. That is a reality. So we're going to look at pervasive computing fundamentals and smart devices. Now, these smart devices are part of the Internet of Things, because if they connect, now they are on the internet. Okay? They're on the internet. So we're going to be looking not only at devices as components, physical components, but also services. Services are important as well. Things like tagging, sensing, controlling different things. So these activities, and as a good example of pervasive computing systems, we're going to look at autonomous systems. And the most relevant, we have had some type of, lots of different autonomous systems for a while, okay? For a while. It's just the extent of autonomy. How autonomous have they been? But the one that is kind of the lightning rod is the self-driving vehicles. So we're going to try to talk about that And when I say, I shouldn't say self-driving vehicles, it's really autonomous transportation systems, because it doesn't really, it's not a stretch to think that if your cars are smart enough to know when to stop, when to turn, when to go, and they are connected, they should be smart enough to talk to each other and negotiate passage. So why do you need traffic lights? Okay? So smart transportation systems. So that's part of that chapter. And then this is the chapter where we talk about systems and software engineering and the relationship in the context of cyber-physical systems. So again, we're going to revisit a little bit of the systems engineering. What are the design challenges? So this is probably the chapter that is less about technology, more about methodology. Methodology and discipline, they are very important. They're very important in bringing to life complex systems. As I mentioned, 65% of the projects are late and over budget. Only about 10% meet the requirement. The other 25 fail. Okay? Because they're so late and so over budget that they fail. So it is necessary to have good discipline, good processes in place, and to put together these complex systems. Now, for some of you, if you are an electrical engineer, this would be very good for you because you haven't been exposed to software engineering. I'm not talking about a language. You can pick up a language and start coding, but the discipline of software engineering, you haven't been exposed to that, so this will expose you to that a little bit. Your colleagues in computer engineering, they do have a whole course about that, but this would be, so they'll be familiar with that part, but it will be a reinforcement, but for electrical engineers, it would be a good, great new knowledge. And in the context of software design, again, the importance of requirements. So this is the chapter that deals mostly with methodology. And like I said, then we're going to close the course talking about the sort of the biggest cyber physical system that you can conceive, which is this smart manufacturing industry 4.0. So we're going to give you an introduction to manufacturing. I talked about individualized production. So if you can make it custom at a high quality and low cost, that now you have some very smart manufacturing system, because it's easy to make something unique that is very expensive, okay? Or make a bunch of stuff very cheap. But how can you customize at a very low cost? There are techniques that are coming online that are becoming more and more sophisticated. I mean, the kind of quality out of the high-end 3D printers that you can get today, I mean, it's not something that you can get, in your home right now. But think about a business idea of having this kiosk where it's a high-end 3D printer. And now you can make your own product and go to, the supermarket, get your file, and now you get your stuff that you designed, an hour ago. If the software is easy enough to allow that, and you don't have to be like a CAD expert. But systems, complex systems that enable low-cost, individualized production. Now, these smart factories, a key to them is the transfer of knowledge and the cooperation of the entities in that factory, and that's going to take networking and connectivity. So we're going to talk about different types of manufacturing lines, And in that context, also the importance of cybersecurity, because those systems are going to be the most vulnerable and susceptible to threats. Although all the systems are going to be, like, you don't want someone hacking your self-driving car, right? So, but this is a good part to talk about that, although we'll be talking about that all throughout. So, in a nutshell, that is the course, and we'll come back. We'll come back to chapter 1 tomorrow, and we'll start with the course.